Hello everyone, it is Buket from ICHEC. This is a short introduction to OpenMP loop level parallelism. In this presentation, I will be talking about the topics listed in the outline. We will mainly focus on the parallelization with the loop construct. First, I am going to define the loop construct and talk a little bit about how to combine this with the OpenMP parallel construct. Then, I'm going to describe a couple of common OpenMP clauses, such as reduction and schedule. Then I will talk about the synchronization constructs, master, critical, barrier, and so on, as well as explain the data race condition. At the end of the presentation, I will demonstrate a Monte Carlo example to show how to use random number generators in parallel and very briefly discuss how to measure time in OpenMP. The loop construct is used to parallelize computationally intensive loops in a sequential program. It is one of the work-sharing constructs of OpenMP. It is used to distribute loop iterations over the threads in a team. The compiler then decides how to map these iterations to threads. During the parallel computation, communication between threads is implicitly done through data sharing. Loop directives don't create new threads, but assume that a team thread has already been created. The C++ loop directive is pragma-omp4, while the Fortran loop directive is omp. Data clauses, reduction and ordered clause, can be used with the loop directives. By default, there is a barrier at the end of the loop construct. You can use the no-wait clause to turn off the barrier. You can see from these syntaxes that a parallel region has already been initiated before using any loop directive. Otherwise, the program executes in serial on a single processor. Basic approach when working with loops is first finding the most time-consuming loops in the sequential program and then adding OMP loop directive. In the illustrated example on the left, we have a for loop of 1000 iterations that does a huge computation. The OpenMP version is illustrated on the right. We first create a parallel region to divide the work into team threads, then parallelize the computation by adding pragma-omp4. Inside the parallel region, the iterations will be distributed among threads. Sometimes, transforming a sequential for loop into a parallel for loop may not be as straightforward as this. There are several performance considerations to take care of in order to take full advantage of the parallelization. The most important one is to remove data dependencies so that threads can safely execute in any order without loop carried dependencies. Parallelizing a loop with data dependencies causes data race conditions. In the piece of code on the left, we see that two rows may not be updated simultaneously because there are data dependencies between rows of the matrix A. You can see that in order to update the row I, we need the entries of the row I-1. However, the columns may be updated simultaneously, so the loop indexed by J may be executed in parallel, but not the loop indexed by I. If we invert the loops, we can get loop parallelization without data dependency. However, there is another issue arises here. Since matrices are stored in row measure order, which means that all of the values in a single row of a matrix are stored next to each other. Inverting loops may cause cache miss. So, cache miss is another performance consideration when working with loops. We now illustrate the parallel matrix vector product of the form y equals A times x. We store the matrix A as a one-dimensional array and use proper indexing in order to get the necessary row and column entry. Essentially, the matrix vector product corresponds to multiplying the ith row of A with the vector x in order to find the ith entry of the result vector y. This is simply a dot product at each iteration I. Here, no two dot products compute the same element of the result vector. Moreover, the order in which the values for the elements I are calculated doesn't affect the correctness of the result. So, this problem can be perfectly parallelized over the index value I. We first insert a parallel directive to define a parallel region. The vectors and the dimension variable are shared data, since all threads need to know the values of these. On the other hand, loop indices, sum variable, and thread ID are thread-specific variables. Each thread will access, for example, the same vector x, but will have its own distinct variable sum. After defining data clauses, we call OMP getThreadNum function to return the thread ID. We then insert the loop directive for parallelization. Note that this loop directive only affects the next statement. We compile the codes by the Intel compiler, respectively by using -OpenMP flag. Then we set the total number of threads to 4. To illustrate how threads share the loop iterations, we basically assign 16 to n. In this case, the matrix will have entries from 0 to 255, and x is a vector of ones. In the output on the right, each thread means it is thread ID and the component of the y vector it calculated. We can see that the 4 iterations are distributed in equal sized blocks to each thread. Iterations from 0 to 3 are handled by the thread 0, and the sum values found at each iteration is written to the corresponding y. Combined constructs are shortcuts of parallel construct plus a work-sharing construct. OpenMP provides 3 work-sharing constructs to be used together with the parallel construct. They are parallel for, parallel do, parallel sections, parallel work-share. Note that the last one is for Fortran only. These shortcuts behave identically to an individual parallel construct followed by a separate work-sharing construct. For instance, for the loop directives, pragma OMP parallel for is same as writing first pragma OMP parallel and then pragma OMP for. Most of the rules, clauses, and restrictions that apply to both directives are in effect. However, there are some incompatibles, such as the no-wait clause. This slide shows the C, C++, and Fortran syntax for the parallel loop construct. The main advantage of using these combined versions is readability. There is also performance advantage. When this version is used, a compiler knows what to expect and may be able to generate a slightly more efficient code. For example, it will not insert more than one barrier at the end of the region. Now I will introduce the reduction clause, which is a commonly used OpenMP clause with the parallel loop construct. The reduction clause performs a reduction operation on the variables that appear in its list. All you have to do is to specify the reduction operation and reduction variables. Variables in the list must be scalar variables. They cannot be array or structure type. The list variables are shared by default. When you use the reduction clause, a private copy for each list variable is created for each thread. Compiler finds the reduction operations and updates the private copy. At the end of the reduction, private copies are reduced into a single value and combined with the original global value. The reduction operation applies to only 4 parallel and sections constructs. It can be arithmetic, such as plus, minus, and times. Logical, such as and, or, for both C, C++, and Fortran. Intrinsic functions, such as max and min, are also possible for Fortran. We rewrite the OpenMP version of the matrix vector product by using the reduction clause. We also illustrate the combined parallel for construct here. Note that this time we parallelize the inner loop of the matrix vector product, which corresponds to dot product of each row of A with the x vector. The vectors y, a, and x, the dimension variable n, and the I index are automatically shared data. The reduction variable sum must also be declared as shared. So we use default clause as shared here. On the other hand, loop index j and the thread ID are private as before. Similar to the previous example, we assign 16 to n for simplicity. We just show the output for I equals 0. The first row of A has entries from 0 to 15, and the x is a vector of ones. The output shows the product of row 0 of A with the x vector in parallel. Each thread calculates a sum value by using the reduction clause at the end of the parallel for construct. All threads will add their values of sum to update the global copy, and they produce 120 for y0. The schedule clause is used only within the OpenMP loop construct. It describes how iterations of the loop are divided among the threads in the team. Type here denotes the kind of scheduling, and chunk stands for the size of iterations. Chunk value must be an integer. There are basically 5 scheduling types. Static is used to distribute blocks of iterations of chunk to each thread. Dynamic allows each thread to grab chunk iterations from a queue until all iterations have been distributed. Guided allows threads dynamically grab blocks of iterations which are large at the beginning and brings down to size chunk as the calculation proceeds. When a runtime is used, chunk size is taken from the OMP schedule environment variable. The default scheduling is implementation dependent. Before discussing some of these in detail, we would like to mention one more clause used within the loop construct. The ordered clause specifies that the iterations of the loop must be executed as they would be in a sequential program. When the static scheduling is used, iterations of the loop are divided evenly among threads. If a chunk size is specified, the work is distributed into chunk-sized parcels. If there are n threads, each does every n chunk of the work. In the illustration, a vector of size 36 is divided into chunks of size 3. Here there are 4 threads. Chunks are respectively distributed to threads. For example, thread 0 will get elements from 1 to 3, 13 to 15, and 25 to 27. The dynamic scheduling divides the workload into chunk-sized parcels. As a thread finishes one chunk, it grabs the next available chunk. When no chunk is specified, it defaults to 1. In the illustration, a vector of size 36 is divided into a chunk of size 1 and dynamically allocated to 4 threads at runtime. The dynamic schedule is appropriate for the case when you don't know the iteration count or there is an unpredictable amount of work. It has more parallel overhead than the static scheduling, but potentially has a better load balancing. When guided scheduling is used, iterations of the loop are divided into chunks such that the size of each successive chunk exponentially decreases. Chunk here specifies the size of the smallest chunk size. If you don't specify a value for it, the default value is 1. In the illustration, a vector of size 36 is divided into chunks of decreasing size and allocated to 4 threads in a round-robin fashion. It starts with large chunks of iterations and ends with small chunks of iterations. OpenMP provides a variety of synchronization constructs that control how the execution of each thread proceeds relative to other team threads. The role of the synchronization is important in OpenMP in terms of memory usage. It is used to avoid from data race conditions. Race conditions occur when multiple threads update the same memory location simultaneously, which causes unexpected and results. But synchronization constructs are expensive in terms of execution time. So it is better first to change how data is accessed to minimize the need for synchronization. We will now briefly go through the synchronization constructs listed in the slide. The master directive denotes a region of the code that is only executed by the master thread. All other threads on the team skip this part. The critical directive specifies a region of code that must be executed by only one thread at a time. The optional name you can see in the syntax enables multiple different critical regions to exist. All critical regions without a name are treated as the same section. The barrier directive synchronizes the thread team by causing them to wait until all other threads have reached to that point in the code. All threads then continue executing the code in parallel, following the barrier. The atomic directive is a special case of a critical section that can be used for certain simple statements. It ensures that a specific memory location is accessed atomically, rather than exposing it to the possibility of multiple simultaneous reading and writing threads. An atomic statement after OMP atomic pragma must follow a specific syntax. For example, in C, C++, it can be in the form of X binary operation equals scalar expression, where binary operation is among plus, minus, times, and so on. In Fortran, it can be x equals x operator expression, where operator can be either arithmetic or logical or intrinsic. The flash directive identifies a synchronization point at which the implementation must provide a consistent view of memory. Thread-visible variables are written back to memory at this point. The optional list contains a list of variables that will be flushed in order to avoid all variables. A flush directive without a list, executed on a given thread, operates as if the whole thread visible variables will be flushed. The ordered directive specifies a region of code in a loop which will be executed in the order of the loop iterations. The ordered directive can only appear in the context of a for or do directive with the ordered clause. Then, iterations of the enclosed loop will be executed in the same order as if they were executed on a serial processor. Now we will talk about the calculation of pi using the Monte Carlo method in OpenMP. Monte Carlo methods are stochastic approaches based on the use of random numbers and probability statistics to investigate problems. They are applied to many research areas, including financial analysis, nuclear physics, population dynamics, and weather prediction. One of the fundamental properties of Monte Carlo methods is the generation of random numbers. The goal is to simulate a realization of a sequence of independent, identically distributed random variables distributed uniformly in a domain. They are very easy to program on parallel machines because each processor can evaluate the function independently on a subset of the given domain. We consider one quadrant of the circle with a diameter r inside a square. Imagine throwing darts randomly within the square. Then the chance of hitting the circle, shaded in blue, is proportional to the ratio of the areas of the circle and square. The area of a circle is pi r square, so the shaded area will be pi r square over 4. The area of the square enclosing it is r square, so the ratio will be pi over 4. Assume that r equals to 1 and the circle is centered at the origin. For each throw, we generate two numbers between 0 and 1 corresponding to x and y coordinates. We calculate the distance from the origin, which is square root of x square plus y square. If the distance is less than or equal to 1, then it is hit. Finally, to calculate pi, we multiply the total number of hits over the total number of random numbers by 4. Here is the C code. The iteration index is defined to be private and the reduction operation is applied to the hit variable. Note that it was globally defined to be 0 before the parallel region. Moreover, since x and y are defined inside the parallel region, they are automatically thread private data. The iterations are dynamically divided among threads by the dynamic scaling. Each thread first randomly assigns a value to x and y, and then checks if x squared plus y squared is less than or equal to 1. After the parallel region, an estimate value for pi is calculated using the total number of hits of all threads. How good it is depends on the total number of iterations. In other words, on the quality of the random number generator. As you can see from the output, a better estimate can be found as the total number of iterations increases. This is another version of the same program. Here we use critical directive instead of reduction clause. We first create the parallel region. We now have another hit value which is a thread specific value. It is t hit variable. Inside the for construct, each thread adds to that value. We can see from the output down here that, for example, thread ID 0 has 22,484 number of hits at the end. After the iterations complete, we create a critical section. Each thread enters to that section at one time and the thread hit value. At the end of the parallel region, we get the total number of hits. Finally, in this presentation, we will shortly mention timing with OpenMP. OMP getWaitTime function is mostly used for wall clock timing. It returns a double precision floating point value equal to the number of elapsed seconds since some point in the past. It is usually used in pairs with the value of the first call subtracted from the value of the second call. Note that it is designed to be per thread times and therefore may not be globally consistent across all threads in the team. The OMP getWaitTick, similar to OMP getWaitTime, returns a double precision floating point value equal to the number of seconds between two consecutive clock ticks. These are the references used to prepare this presentation. Thank you for your attention.